Hi, this is Anthony Chirico, and today I'd like to talk to you about reverse engineering your experiment to be more efficient and to be more effective. This is what they never taught you in your black belt training. We'll take a typical one-way analysis of variance and analyze it in the traditional fashion, and then we'll take that same experiment and reverse engineer it, and you can see for yourself how much more effective reverse engineering can be. So now we'll conduct our one-way analysis of variance in the traditional fashion. We have three different machines that we want to compare, designated as K, and we'll take 30 observations from each machine. Little n will designate the observations within each machine. So there's a total of 90 observations. The large N equals 90. So we lay out our traditional one-way analysis of variance table as you see here, comparing the between machine variation to the within machine variation. We've calculated our sums of squares, degrees of freedom, mean square, and our calculated F statistic. So we've done all the hard work. We've randomized the experiment, we've thought it through, we've collected all the data, and then we've either loaded the data into a computer program or we've started to do this by hand if you're old school, and then we'll look up the critical value. I've chosen an alpha risk of 5% with the 2 and 87 degrees of freedom as shown. And then we see the critical value by magic is 3.1. So in this case, our calculated F statistic 3.74 exceeds 3.1, so we will reject the null hypothesis that the averages are equal, and we'll embrace the alternate hypothesis that the averages are not equal, and we'll go off now patting ourselves on the back and trying to discover which machine is different from the others. So the point is that you've run a very expensive experiment. You've collected all the data, you've randomized this experiment, maybe you even had to stop production for a little while. You run through the analysis, and it isn't until you're in the analysis phase that you discover what the critical value of F is. The critical value is like the height of the bar that you need to jump over, and you never know what the height of the bar is until the very last second. It's a bit of a surprise. So now let's look at a better way. In this illustration, I have graphed for you the actual critical value of F with an alpha risk of 5%, 2 degrees of freedom in the numerator, and large N minus K degrees of freedom in the denominator, and that is what's illustrated on the x-axis as the variable in this function. So by observation you can see this is not a simple linear function, and there's a rapid decrease in the critical value in the very first few degrees of freedom, followed by a very flat section from about 19 degrees of freedom all the way out to infinity. In fact, the value at infinity is just less than 3. So this is extremely flat after about 19 degrees of freedom. So we use this function to help us to size the experiment. We know that we want to study 3 machines. We can take 2 observations for a total of 6 runs, or we can take 3 observations for a total of 9 runs, 4 observations, 5 observations, or 6 observations, and this will size our experiment to 6, 9, 12, 15, or 18 total runs. So from here, we can use this information to calculate the degrees of freedom that are required. So the 6 runs minus 3 machines will give us 3 degrees of freedom. 9 runs minus 3, 6 degrees of freedom. 12 runs minus 3, 9 degrees of freedom, and so on. 3, 6, 9, 12, 15. And so we can lay these degrees of freedom right on top of the graph to give us a visual representation of where this falls. And we can see here that 15 degrees of freedom is the blue vertical line furthest to the right. And in this case, we're very close to the flat section of this curve. So it would make absolutely no sense to have an experiment that's any larger than 15 degrees of freedom. So we'll take this point as our design point, and the critical value of F is known, 3.682. So before we even run the experiment, before the experiment's even designed, the very first thing we do is to establish the critical value of F. Simultaneous with that, we have designed the experiment. It's not just an arbitrary choice about what the sample size is. We know we want 3 machines. We know we're going to take 6 observations at each machine. The size of the experiment is going to be 18 runs. The critical value is 3.682. This is the bar. This is the height of the bar that we're going to need to jump over in our experiment in order to reject the null hypothesis and embrace the fact that the machines are different. So we run this experiment, as I said, and now we lay out the analysis of variance table. The very first entry in the analysis of variance table is the critical value of F. It's not the last entry. It's the first entry. This is not a surprise entry. So we lay in the degrees of freedom, and the mean square will be different, or pardon me, will be the same as previous, because the variance between machines and the variance within machines doesn't change. The F value we calculate, and once again, as in the previous example, we reject the null hypothesis because 3.74 is greater than the critical value of 3.682. So this experiment is actually 5 times more efficient than the initial study, because it only required 18 trials versus the 90 trials in the initial experiment with the same conclusion. So I hope this illustrates the effectiveness of reverse engineering. So what are the takeaways? First, set your critical value in advance of running the experiment. The critical value is the bar that you need to jump over in order to reject the null hypothesis and conclude that the things that you're trying to study are actually different. So set the critical value as low as possible, but yet there's no need to run a large experiment because you understand the shape of the function of critical values, and you try to avoid that long flat section of the curve. In our example, 15 degrees of freedom hit the sweet spot. It was a good trade between a low critical value and a efficient size of the experiment. So number 2, once you set the critical value, this in turn will size the experiment for you. So do this all up front. Don't let the critical value be a surprise at the end of your analysis. So reverse engineer for success, and happy experimenting.